and I'm talking today about Docker offshore packaging applications for hard-to-reach data centers. Ah, yes. Which button?
Forward and backward.
Ah. Yeah. All right. A little bit about us. Andrzej already had the presentation today about us, so I probably don't need to talk so much about us. We are about a little bit more than 30 IT consultants. We have offices in Berlin and in Warsaw, and the core areas of our expertise are stuff like cloud consulting, helping companies getting production workloads into the cloud. We do this mostly on AWS. We also do architecture, we also do development, and we are doing operations. And typically for the stuff we develop, we have the same people who have the developer roles, they are also in the operation role. So to understand a little bit about the changes I'm trying to tell you about in this presentation, it's useful that I tell you first about our preferred mode of operations. Usually we do everything on infrastructure as a service. So for us the advantages are very clear. It helps us to manage risk by getting all the developers into the hands of the correct people, of the people who are actually going to have to work with the stuff. We are not running into the risks of underestimating or overestimating the requirements we have, the resources we need. And because typically the big infrastructure as a service providers are kind of at the forefront of innovation in our sector when it comes to the ability to express everything about your environment as code, which is very, very useful for us because our developers also are the operators of the software we manage ideally. So for them it's really useful not to have anything that is non-deterministic. Everything is expressed as code, everything is version controlled. So a typical setup would be something like we have a project that is running on AWS, so we define the whole infrastructure using CloudFormation templates. That means we can use the features of AWS CloudFormation to provide software-defined networking. So we have network topologies, we define databases, DNS records, security rules, so kind of software firewalls. We define auto-scaling groups and launch configurations which basically describe a number of virtual machines. And the stuff that is going on with these virtual machines is also described by a tool chain, which is automated, which can be checked into code, and which does stuff like building images, and on these images, provisioning software is run. Stuff we all know about in one capacity or the other, stuff like Chef or Puppet or Ansible. I don't think we use Salt, but all the other three are used in some in some projects. And of course, one of the requirements for this kind of setup is that you have internet. I mean, this sounds like a really simple requirement, but when you're deploying software to infrastructure as a service, you typically do not think too much about that, because internet is cheap, bandwidth is not a problem, latency is not a problem. There are, however, at least two places I could think of where these rules do not apply. And unfortunately, I'm not talking about the ISS today, but about ships. So as far as I know, every presentation about Docker needs to feature the image of a container ship. So here it is. I'm not talking specifically about container ships, but about ships with large data centers on board. And when you talk about data centers on ships, the situation is not so easy anymore. Because when these ships are offshore, internet is almost never fast and it's almost never reliable. You can expect stuff like ranging from a few megabit per second to, under very specific circumstances, depending on the location and the type of equipment which has been installed on the ship, stuff like maybe, under ideal circumstances, 350 megabit per second using OTB, which is a relatively new satellite constellation which only operates in a small band on this planet. You can expect latency from multiple seconds to something like maybe 200 milliseconds. And you can expect to share this bandwidth with thousands of consumers. Even if you have something like the idea in the ideal cell for OTB, this stuff is never cheap. And something that may happen is that if the ship is in a harbor In certain harbors, and depending on the type of the vessel, you might have broadband, maybe. So the internet environment you can expect on data centers that are on a ship. The quality of this environment, it depends on various factors. It depends on the age of the vessel, it depends on the location. It can even depend on stuff like geopolitics. So if, for instance, there is a humanitarian crisis and lots of journalists are around, or a military convoy or something like that, you will have to share your bandwidth with them. So this is really complex. And the other complex part is, on the slide before, I talked about bringing control to the developers. Yeah, well, data centers on a ship are almost always subject to complex regulatory requirements. And this is independent of the software that you're running. So if you deploy software that is dealing with credit card data, for instance, of course you would be subject to specific regulations. You would perhaps need a PCI certification or stuff like that. On ships, the situation is that it's always much more difficult to do things in a DevOps way. So we have many environments, in fact. Even if we are just talking about one ship, if we have the situation we want to deploy a certain class of software to many ships, we have factors like what is the age of the vessel, where is the vessel. We also want to deploy this software that is running on the ships to regular data centers. So in fact, we have many different environments which we are dealing with and where we have to run our software. And the problem is under these circumstances is that we cannot really do stuff like ship VMs. If we were to ship VMs, we would breach the separation of roles that is sometimes required for the regulations, for us to comply with the regulations. So the VMs are provided by the operators of the data center. And our regular provisioning tool chains cannot really guarantee deterministic behavior under these circumstances. Because it's always a little bit like, okay, I want to run this chef recipe, fingers crossed that nothing goes wrong. And in some cases, because, I mean, as soon as these tool chains grow to a certain size, they're complex software in themselves. So this is also stuff that the operators would have to run. And if you want to debug a system which is in a state that is not really deterministic, and you cannot reach the data center, and you want to debug this from remote, this is not a good situation to be in. So the current tool chain is like a little bit how we did these things in the past. It's not particularly spectacular, I think. It's... Am I blocking the wheel? No, okay. We are doing code management and reviews with GitHub and GitHub Enterprise. We're doing continuous integration with Travis Pro, which is the software as a service version of Travis. And we are using Atlassian and Bamboo also for continuous integration. And provisioning is typically done with Puppet and Chef, depending on the age of the project. As you can imagine, in such a setup, continuous deployment is not really an option. So what we did instead was the results from our software delivery pipeline was we were building packages, packages for our own software, packages for the runtime requirements. Then we were provisioning these runtime requirements and these and the custom packages for our software. And then there was a manual deploy. So pain points we had with this thing became quite obvious after a while. Every environment needs somewhat custom provisioning, and we cannot get an easy way for achieving deterministic state changes in these environments. And as I said before, the longer you are managing a non-trivial Puppet or non-trivial Chef configuration, the more it becomes complex software in itself. So you're maintaining complex software to manage the runtime requirements for your complex software. And yeah, this is of course a little bit painful too. On top of that, we had to package like everything. Because when you look at the politics of long-term support enterprise Linux vendors, they pose a fundamental problem for us as developers. Because if you buy into an enterprise long-term support Linux, you will not be able to have your cake and eat it too. Because if you want to stay on one version of your operating system for a very long time, which is kind of the point of long-term support, then you will not be able to get very recent versions of your software. So if you're running on Red Hat Enterprise 6.5, for instance, then you're not going to get a brand new version of Redis. Like, no way. You have to package all that stuff and their dependencies too. So, in the middle of last year, we began to invest a little bit in the future stack. We had to begin using Docker 06 for internal tooling. So we already had some experience with Docker for productive workloads. And we quickly figured out that shipping our software with Docker into these kinds of environments would reduce the amount of provisioning we would need. So the amount of tooling we would need to satisfy the runtime requirements of our software. This would reduce it to almost nothing. Not because we had no more need for provisioning, but because provisioning became part of the package we shipped. So we had not many small packages and needed to integrate them into the enterprise Linux environment. Instead, we shipped a Docker image which contained everything we needed, with a Linux version that was not necessarily the version that these Docker containers were run on. What we also gained was that we didn't have anymore this problem with having to deal with multiple environments, because what Docker basically gives you is the ability to share an immutable build of your software. So you put in all the packages, you build your image package, which can become a container when you run it on the Docker host, and this thing is immutable. We never changed this as soon as we gave it a certain name and a certain version and basically published it into our continuous deployment toolchain. So we have an immutable build, so we know at all times what is really going on, and we have a very standard way of configuring these immutable builds into containers which can work in different environments through environment variables. So in short, no more building and provisioning custom packages, instead package everything with Docker. So, a little introduction to Docker. I've been asked before this presentation to not do this too technically, so tell a little bit more about problems we solved, so I'm trying not to be too technical. Docker is a client-server application which is written in the language Go, which Google has released maybe 2 years ago or 3 years ago, I'm not really sure, which is shit. Which yeah, I mean, ironically, Go is an ungoogleable name. You cannot Google Go, so often it's spelled Golang. But what this client server does is it provides userland virtualization. And userland virtualization is not so much a virtualization of hardware layers. Instead, it can be thought of as a virtualization of perspective. So what that means is that software that is running in a container thinks about or can see its environment, and for all practical purposes, from a container's point of view, it's running in a dedicated host. It's not shared. From the host perspective, which is running the container, say you're running 10 Apache containers on one host, the host will see, if you just inspect the state of the running processes with PSXA, for instance, the host will see 10 different Apache processes. Also, compared to the provisioning toolchains we were using before, Docker is not abstract, it's concrete. So I'm never telling Docker something like, okay, I want Apache installed on this host, and I want this service that it represents to be running. And then Chef or whatever figures out, okay, this is going on in this environment, in this operating system. I need to invoke apt-get something, 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 and then I need to hook it up to Upstart or whatever. Instead, to express something like that in Docker, you would need to figure out what the correct command would be for the package manager for the Linux you're packaging. For instance, apt-get install Apache 2, and then just type it. And out of it comes an immutable image which has executed this command. Docker has no concept of changing state from A to B. So Docker is really about producing something immutable. If you figure out that this old state is not needed anymore, then you remove or change the line in your Docker file, and then this line was never executed and will never be in the image that results of that. You can think about Docker as having three logical components: a build component, a distribute component, and a run component. The build component deals with building images. And typically you build these images using a series of commands expressed in something that is called a Docker file. The result of practically every line in your Docker file will be a new immutable image, which is a snapshot of environment state and a snapshot of file system state. And every line in your Docker file is able to see the result, the state changes to the environment and the state changes to the file system of every step before that in the Docker file. So you can think of those immutable images as layers which are layered on top of each other. So the stuff at the bottom of your Docker file sees everything that has happened before. You have a number of commands you can express in a Docker file. There are not so many. For practical purposes, we can limit ourselves during this talk to add and run. Run executes something in the operating system you're building your container from. And add is something which deals with context. Context is basically everything next to your Docker file. As I said before, this is a client-server application, so when you run it with a Docker client, it uploads everything next to your Docker file to the server, and you can add everything you had next to your Docker file as an immutable image, another immutable image, to your series of image layers. You also have caching. Docker will cache every line in the Docker file based on certain conditions. That means, effectively, if you rerun your Docker build and you have changed nothing, then the build will complete instantly because it caches every line. This also means if you just change a few things in your Docker file, it will only build those lines you've changed. The distribute component is about naming images and being able to push and pull them to a repository called in Docker lingo a registry. So you can apply names to images, and names consist out of a product name, can consist out of something that is called a tag, which can be a version number or a Git a Git commit ID or a code name or whatever. And in a name can also be something that looks like a URL. And Docker has a natural mechanism of being able to push images to these repositories and pull them from there. And the same caching mechanism applies also. That means if you pull something from a Docker repository and you pull again, it does nothing because it has pulled all the images again. So that means for a release, if I push a release, I've changed maybe the last 2 lines in my Docker file. And if I want to distribute this release and I have pulled this stuff before, it will only pull the last 2 new layers. The run component deals with making a process out of this union of environment snapshots and file system snapshots. And you can express in your Docker file in one or 2 ways. You can express what kind of container what kind of process should be started inside this union of file systems. And what happens next is you have this process that's running in the foreground, which makes a container out of the images, and on the bottom will a read-write layer will be inserted by Docker. So the container has a way of persisting state during its runtime. So the net result for us was we had a very, very easy way to name things, to build a very easy way to restructure our packaging and provisioning system. We had a very easy and convenient name of a way of naming our applications, because in the name were lots of interesting meta informations. For instance, we had a version number, a logical version number. We had a Git revision ID. We had a tag or something like this is for production, or this is the beta 1 or whatever. And we had also a very simple way to distribute those packages. The results from those Docker builds are immutable. They are not exactly reproducible. That means that you really need something like those repositories. like binaries, when you build binaries or complex binaries in C or C++, you will also not be able to reproduce them if you build them on a little bit different machine or after a few updates. But you can nevertheless put them in a repository, sign them maybe, and if you download them, you can be sure, okay, this is exactly the same thing. And another very interesting aspect of introducing Docker as our alternative packaging and provisioning toolchain for these environments was that we were saving valuable bandwidth and space because we only have to synchronize the diffs if we pull in changes. There are two special cases I might talk a little bit about, but the time is always, I don't know, did I start at 14:30? How much time is left?
You still have 10 minutes.
Okay, I still have 10 minutes. Okay, then I'll talk a little bit about the special case of dependency managers. Dependency managers are a little bit special. Dependency managers are stuff like, for instance, bundler. I guess people here in the audience are deploying projects like Rails projects and stuff like that, probably. So bundler is a little bit special because bundler, or all the dependency managers are, they expect to be a little bit more like Chef or Puppet. They expect to have this repository of dependencies at a special location, and when you change a little line in your gem file, for instance, and you run bundler install again, then bundler will only execute the changes because everything else was there already. With Docker, this kind of doesn't work anymore because your call to bundle install will be in one line in your Docker file. So if you just change a very small thing, it will nevertheless result in a new image, a completely new image, which is a bit problematic, of course. When you're running Rails, you will probably have a few dependencies which require C code and stuff like that, so the build takes a while, and it will also be quite big. A couple of megabytes, or maybe tens of megabytes, maybe hundreds of megabytes. It really depends. There are various ways to work around that, but it's nevertheless nothing that is super obvious when you use Docker. Patch management is also an interesting area because typically if you are not delivering hotfixes for your software, there are sometimes circumstances when you need to patch your runtime the runtime requirements of your software too. Contrived examples, let's say for instance you had the urgent need to patch something like Bash or OpenSSL. Maybe. Yeah, maybe. It's just a contrived example. Typically these things would be pretty much at the top of your Docker file. Because let's say we want to package a Rails application with Docker, and we want for some reasons also to do this with RVM because we're using RVM on the developer machines too. Okay, let's say that. OpenSSL needs to be installed before RVM. So install OpenSSL, then install RVM. This takes ages and ages and ages, and then install your Ruby application, bundle your gems, etc., etc. So you will have to change a line pretty much at the top of your Docker file, which means you will have to ship all the new images that follow after that, because when you change this line, the cache invalidates everything that comes after that. So we will have to ship something very huge just to deliver this small patch. What you can do instead with Docker is you can take the last known version and then run this little patch and ship just the resulting image. Of course, at some point you would need to deliver the newly changed build where this has been inserted at the appropriate place. But the good thing about our environment is that we have something very natural, a separation of roles if desired. We have a very, very easy way to say, okay, this part of Docker is the responsibility of the developers, and this part of Docker is the responsibility of the operators, which is something we need on the ships. And the operators have, because the job of the operators is to do stuff like pull in a release. Say, okay, now we want to update to this and that release. And they can also decide, okay, now we need to pull in the patch. And we can communicate, okay, this patch we will need to release something new, but this thing will be 500 megabyte large. And then they can decide, okay, now is a good opportunity to do that, or now we're in this and that harbor, and at this point is a good opportunity to do that. So running containers is something very simple. Running containers is, in case of the ship environment, something that is done by the operators. They pull a release, They start a container out of such a release. They are responsible for maintaining the environment key and value pairs that are pushed into the container. Stuff like the URL for a database or names or tokens or passwords or something like that. This is not part of the images. This gets configured to the runtime environment by passing in a start script certain environment key values. The interesting question is, if you think about the problems we had with the long-term support Linux politics and the packaging of custom packages, or the question really is, what's left in a host operating system if we package everything with Docker? And there are two projects I'm aware of right now, that's CoreOS and Atomic, that are kind of thinking about this idea and have already delivered quite amazing products, I think. In the case of Atomic, I'm not 100% sure if it's really amazing because I've never played it with myself, but at least the documentation is very good. If you say, what is the role of my host operating system and in the presence of Docker, the most natural intuition would be, yeah, there is nothing to do. Because when everything that's really relevant for the services you're going to deploy over the host operating system is in a container, CoreOS and Atomic try to solve different problems. For instance, patch management. CoreOS is auto-updating capable. CoreOS, when run in a certain configuration in a cluster environment, can do stuff like you have a cluster of 5 CoreOS instances. One of the instances detects, okay, I'm a little bit too old. And it's written, it's deployed in a read-only part, or in a read-only way using BTRFS. So all the changes you're writing to CoreOS are not really ending up on the same file system that the image is coming from. So CoreOS can do things like that. Okay, I want to update. I negotiate over a distributed key-value database with all the other members of the cluster. I negotiate that I want to reboot now. I'm evicting all my containers to different nodes, or they're evicting themselves, more correct. Then I reboot, try to apply the update, and if the update applies okay, then I'm back in the cluster and get back my nodes. And it can even do fallbacks. So the update failed, then it rolls back to the last good known state. So these are very interesting developments. Atomic, for instance, is backed by one of the bigger enterprise long-term support Linux vendors, by Red Hat. So it's definitely interesting what is going to come out of that in the future. So one step back on your tool chain, nothing has changed. CD is almost there. We are using Kai.io, recently rebranded to CoreOS Enterprise Registry and Bamboo and a Docker private registry. What you can do with stuff like Kai.io and also with the commercial offering of Docker, which is called Docker Hub, is you can easily build your images out of commits to, say, GitHub. So you push something to GitHub, and these tool chains will build you images for the diffs, and you will have a registry where you can pull stuff from to deploy it. And they will automatically tag those images with stuff like the branch, stuff like the Git revision, and you can very easily release your software this way. So, to summarize what is gained, we have gained concrete instead of abstract provisioning, which is maybe not much of a gain, but it helps tremendously by getting people on board with this technology. It helps tremendously not to require to contextualize yourself with a specific way, this and that Puppet version, which we stopped trying to update to another version long ago because it's probably not worth the trouble. It's much easier to understand what's going on if you just have to look at a Docker file which contains a bunch of operating system specific calls. It's also much easier to Google that stuff instead of Google what is going on in my company's custom Puppet toolchain. This will probably not yield many useful results. And we gained identical immutable builds which we configure at runtime for different environments, which allows much more easier determinism. And of course, no more packages, no more custom building of packages and their dependencies for enterprise Linux. And a simple separation of duties, something that was not artificial, which we had to think about, but instead something that came natural out of the tool chain. Questions, please.
Thanks. Your example of deploying to ships in the middle of the ocean is very, very different from a problem that a lot of us probably struggle with, but I'm wondering if you think it's a...
Can you talk a little bit louder?
I'm sorry. I'm wondering if you think it's a good solution for keeping developer...
Once more, please.
Do you think this is a good solution for keeping developer environments up to date on just developer laptops? Some of us support, 100 developers, and they want the latest version of a continuously deployed application on their laptops. So you have, lots of Vagrant environments running around. They get out of sync very, very quickly. They have a whole host of problems. Do you think deploying Docker images from a private repository is a good solution for that problem?
This is really, really hard to answer in general. I mean, for me personally, Vagrant is an amazing tool, which, if it works for me, this is really nice, and I can do lots of things. I'm working on a little bit restricted environment on a Mac, and many things do not work, of course, on a Mac. Linux, Docker is currently Linux only, for example, or this Docker server is Linux only. But the problematic part of Vagrant is initially it came to the market with a promise of that you will never have again this works on my machine. Yeah, it has been replaced, at least in my experience, with Vagrant is not working on my machine. So I mean, maybe other people have different experiences, but I find it increasingly difficult to find the exact configuration to get everything running with Vagrant also on my colleagues' machines with stuff like shared folders or networking or all other kinds of things. I think you can integrate Docker without too much pain into developer workflows because it basically tries to solve the same problem. And on top of that, you will be able to really share the same environment on the developer machines with the production machines. It will be the very same.
So part of the problem is that VirtualBox and Vagrant, the developer checkout and developer copy of the production environment goes out of date very, very quickly from the software. And so, developers are working on a new feature and they just want to rebase their code to current, master whatever.
Yeah. The good point is that you can replicate the environment extremely easy because really nothing stops you from using a base image for your Docker image that is actually just regular Linux that you can run, for instance, in VirtualBox, or you can run it in Fusion or whatever. You just run that Linux and you use the same environment keys and values, and this is like exactly what will be going on in the Docker container. So I mean, there is really no difference, like none. The only thing, there are very, very few cases I could think of where the container would behave differently than a regular Linux. So since there is no magic going on with Docker, I don't even think that it would be necessary to, in order to get started with Docker in your development processes, to actually work in Docker containers. Just Linux. You're welcome.
Okay, I have another question.
Do you have any experience on portability of those Docker containers between different Linux distros? For example, yourself developing on CoreOS and your customers on those ships running long-term support versions of, let's say, Red Hat or something else?
So far, we have cross-deployment experience with CoreOS, some Ubuntu. What is the latest long-term support thing? Trusty? Is it Trust? 14.10 or so? Whatever. Some Ubuntu, some 14-ish Ubuntu. Red Hat Enterprise Linux 6.5 and Red Hat Enterprise Linux 7.
That's
So
quite
I
impressive.
think it will work in most environments. The only differences are exec drivers and storage drivers, so they work out a little bit differently. But if you pick two Linux systems with the same storage driver and the same exec driver, then you should have exactly the same behavior. Because Docker is really just a packaging for using other APIs to achieve what it achieves. It's not inventing anything new.
Thank you.
You're welcome.
Any other questions, please? Okay. Let run.
I have a questions about practical part of your work. How large are environments you work with, and how do you share state of infrastructure? So if you have some services that you need to bind, do you have hundreds of instances running, and what do you use and how it works?
Yeah. On the environments on the ships, we do not have hundreds of services to bind against. So
So how much Docker containers do you have on these ships?
yeah, I cannot really tell you about this in detail. I'm sorry.
Okay.
But what can you rephrase the question maybe? What do you mean by state
do you
management?
use any service discovery tools?
Service discovery tools.
Yes.
No, mostly not. Because the thing is about the ships and on AWS, yes. On the ship environments, you have the most unelastic amount of computing requirements you can imagine. Because there's a finite number of passengers on the ships, and the operator of the ships tries to maximize this number, so they're trying to keep them at the same level, and everybody has a schedule. So we do not have a need for any kind of elastic solutions or dynamic, or dealing with dynamic workloads.
Okay, thank you.
You're welcome.
Okay, so probably one more.
You said something about CoreOS upgrades and containers moving away to a different host for the duration of the update. I'm only starting playing with Docker, and is it not the case that the containers don't have any state? So
Containers can have state.
but then you have to use volumes, or?
It depends what kind of application you have. If you have a Jira, for instance...
database, let's say it's a...
Databases are tricky. Of course, a database needs to have a special file system, and a database, it's not so easy to migrate a database from one host to the other. If you're talking about a master, of course, there's very special circumstances under which you can migrate a master. If you're talking about slaves for a database, maybe you can get away by migrating them seamlessly. But databases are really tricky. So you can put a database in a container, it's no problem, but you probably cannot migrate them from one host to the other in a cluster setting. And CoreOS offers no magic to help you with that. You could migrate it if you were to store the file system also in a container, and you would snapshot that container and pull the container changes to another host. There are provisions for that, but currently there is no tooling in the Docker ecosystem to support such a use case. But it's just a matter of developing this specific thing. All the tooling is there, it's just not built into a tool yet. And of course you have the problem that clients will not be able to write to master, and this is something that cannot be solved by the operating system or by the packaging system.
Okay. I think we'll leave any other questions that may arise afterwards to the discussion.
All right, dziękuję. Dankeschön.